can start the webinar. Okay, good morning everyone. My name is Xiao Li and I'm an assistant professor at the University of South Florida. Welcome to this TFTC webinar in the ISTTT series, and thank all of you for attending this webinar despite time differences and the weekend issue, and I really appreciate it. So I want to first thank Dr. Jack Haddard from Israel Institute of Technology for his support to this webinar system, Dr. Jorge Lava for his organization, and my student, most impressive for technical assistance. First, I would like to humbly ask you to mute your audio system on this GoToWebinar system. I think I sent a message about it through the chat box. So basically, unless you want to speak or talk to the group, you may want to click the microphone icon on the ribbon to the left, and this is going to toggle the mute on and off. So we're going to have a presentation about 45 minutes or so, and the remaining will be Q's and A's. You can either speak out or use the chat box with which I just sent out a message, a welcome message. And if you want to use the chat box, please make sure that you want to send a message to organizers and panelists only. I'm going to talk about it again when we get there. Okay, so we're gonna record the. We're gonna start the recording at this moment, and the whole process will be recorded for your information. Okay, today we're very glad to have Dr. Ludovic Leclercq, and he is a professor at ISTTT, the French Institute of Science and Technology devoted to transport, planning, and networks. He is affiliated to the University of Lyon. He received his engineering and master degrees in civil engineering in 1998, his PhD in 2002, and his habilitation thesis HDR in 2009. He is currently Deputy Director of the LICIT Laboratory and the head of a research group about traffic modeling and analysis. He served as a scientific counselor for ISTTT in the field of analysis and innovation for sustainable and responsible transport and mobility between 2009 and 2015. His research interests correspond to dynamic traffic modeling and the related environmental externalities. He's a member of the editorial board of Transportation Research Part B and the CACAIE, the Committee Traffic Flow Theory and Characteristics, that's this committee, of the TRB, the International Advisory Committee of ISTTT, and is Associate Editor of Transportmetrica B. He has co-authored 42 publications in top peer-reviewed journals, has supervised 6 PhD, and is currently supervising 5 PhD students. In 2015, he was granted a ERC Consolidator grant in Social Science and Humanities. Today he's going to talk about his work on microscopic traffic dynamics with heterogeneous route patterns. Without further ado, let's welcome Dr. Leclercq for his talk.
Thank you very much for the introduction, and I'm going to start my presentation. So today I'm going to speak about the concept of macroscopic fundamental diagram, but within the perspective to run a dynamic simulation. And the idea of this particular presentation is to try to improve the representation of traffic dynamics within the reservoirs that can be reproduced using a macroscopic fundamental diagram. So if I start my presentation, just to recall briefly the concept of macroscopic fundamental diagram, the idea is that if you look at some particular points within a network, then you can observe what is classically called the fundamental diagram, which represents the traffic equilibrium states at local level. But if you try to aggregate the traffic observation at a larger scale, then you may observe what is called the macroscopic fundamental diagram, which represents the equilibrium relationship between the flow and the density at the network level. What is important to recall here is that the macroscopic fundamental diagram entails three different components of the traffic features. First, the local traffic dynamics represented by the fundamental diagram, also the network structures defined by the topology and the signal timings, and also the route choices. So in my presentation, I will assume that for a given urban region, we can define a macroscopic fundamental diagram, and I'm going to discuss about how we can reproduce traffic dynamics in this region. So let's talk about traffic simulation. So we know that using classical approach, we can develop traffic simulators. Here you have an example of microscopic dynamic traffic simulators that I'm developing with my research team. The name is Simuvia. And if you now look at what you can do using the macroscopic fundamental diagram approach, the state of the art is to represent a urban area using a single reservoir with a uniform accumulation. So, and also uniform inflow and outflow. So the description of the dynamic is quite basic, because you have dynamic inflow, dynamic outflow, and dynamic evolution of the accumulation within the reservoir, but there is no difference depending on the origin or the destination of the different vehicles. Only very recent works are able to distinguish perimeters flow per OD, and I have mentioned in the slides two papers related to this kind of improvements. What I'm going to show that if you keep the original and very simple representation of a reservoir, then you can very simply describe what would be the dynamic of this reservoir. The idea is that the derivative of the accumulation and with respect to time is simply equal to the inflow minus the outflow. But what I'm going to show you is that these representations encompass a very coarse representation of traffic dynamics within the reservoir, and especially a very coarse representation of wave propagation. And this can be, and the problem is exactly the same that's the one we observed when we look at exit flow models using classical traffic flow theory. So let's simply consider that you have a macroscopic fundamental diagram that is represented in this slide on the left bottom corners. So you have the evolution of the speed within the reservoir with respect to the number of vehicles. And let's simply assume that you observe a restriction of the outflow, and the restrictions appear at the at the end of the exit. And what you see on the bottom right diagram is what you get using the classical equation that describe the evolution of n within the reservoir with different side steps. So in black you have the analytical solution that's accounts for the lag between the entry and the exits due to the change of the output, and the purple and the green, the red, sorry, curves show you what you get when you use different time steps. What you observe, especially when you use very small time steps, is that you immediately observe a change at the exits depending on what happens at the entry. And this is because you have a uniform representation of the accumulation within the reservoir. So what you clearly observe here is that you have a wrong estimation of the delay for the traffic wave within the reservoir. What I mean with the wave propagation, that means that if you see a step at the change of the demands at the entry of the reservoir, or a change of the output of the reservoir, then you will see immediately change in the inflow and the outflow. And this is not what we expect, because there is a certain distance to travel within the reservoir, and we should observe proper wave propagation. So if we want to make proper tracking of the internal wave, what we should introduce is the distance traveled within the reservoir. So we have to change the equation and use a refined description of what's happened within the reservoir. So this is definitely the motivation of this presentation. First, I'm going to use some simulation results to show you how the internal dynamic within a reservoir, and especially what are the impact of perimeter OD matrix and internal traffic condition within the mean traffic conditions in the reservoir. And I'm going also to propose a new modeling frameworks to refine the description of wave propagation within the reservoir. So let's start with the first part, and what I'm going to show you is the influence of heterogeneous route patterns on the macroscopic traffic dynamics. The idea is the following, and I'm going to consider a very simple case study, which is a sort of toy networks, but the idea is just to highlight the influence of the OD matrix and also the influence of the internal states of the reservoir on the macroscopic variables of this reservoir. So let's consider this very simple networks with 4 origin and 6 destination, and let's gather the origin, all the origin within one macroscopic origin, and let's distinguish two macroscopic destinations, one for the south and one for the east. So the simulation is simply a LWR mesoscopic simulators with a triangular flow model diagram. There is traffic signals for each nodes, and in terms of route distribution, I'm using a wardrobe user equilibrium. And I'm going to test various input demands and output capacity profile to represent different loading patterns, and I'm going to characterize the global variation of the OD matrix by one single parameters tau, which represent the fraction of vehicles that go to the macroscopic destination 1. And I'm going to focus on the stationary situation of these networks for different network loading using different macroscopic variables, the number of vehicles, the travel production, the mean speed, the outflow, and the mean travel distance. So let's look at different results. First, let's look at the sensitivity of L. L is the mean travel distance within the reservoir. And we know that there is a relation between the production of travel within the reservoir and the outflow. So L is defined as the production divided by the outflow. And what you see on this graph is the different L value for different simulations that represent different loading patterns. So is the fraction of vehicles that go to the macroscopic destination 1, as I said. And you see also that by changing the volume of the demands and also the capacity at the exit, I can have different internal traffic situations that are characterized by the accumulation. And what you can see here is that if you go until approximately 50, 60 vehicles within the reservoir, we are in free flow, and you have a clear relationship between the mean travel length and the value of tau, which is not surprising because in my networks, and just show you again the sketch of the networks, the travel distance to destination 1 is bigger than the travel distance to destination 2. So the OD flow, the global OD flow distribution, definitely define what will be the value of the mean travel distance. And when you increase, when you have more accumulations within the reservoir, you see that the evolution is less clear. But what is important to notice is that the mean travel distance not only depends on the accumulation, but it's depends on the OD matrix. So this is really important when you want to make traffic simulation within the reservoir to have a proper estimation of L, because this is one of the key variables of the simulation. And you see that if you use a constant value of L that you have calibrated for one given scenario, you can have important errors that are when you have some change both in the OD matrix and in the traffic condition within the reservoir. Second result here is to study the sensitivity of the macroscopic fundamental diagram, so the equilibrium relation between the speed and the mean speed and the number of vehicles, and to see if this is you have some evolution with respect to the OD matrix, so again characterized by the single parameters tau. So what you see here is that if you look at the formulation of the speed versus n, you see a quite well-defined relationship at this level, and you see when n1 equal to 0, that means no one's go to destination 1. You have the red dots when n2 equal to 0, that means no one's go to destination 2, that the blue dot. But at this scale, you can say that you have a well-defined relationship. But if you now look into the details, you see that this relationship depends on the distribution between the two destinations, because here on this graph on the top right of the slide, what you observe is the location of the ISO speed. And what you observe is that the slope is not equal to -1, which would be the case if the influence of the OD matrix, if the OD matrix would have no influence. Here the slope is quite lower. That means that the OD matrix influence the relationship between the speed and the accumulation. And this is even clearer if I plot the travel production with respect to n, and you see that in free flow you have nearly the same curve, but if in congestion, you see that you have quite huge difference between the curve depending on the OD matrix you use. And this is simply because here if you look at the speed, you may see that you have not huge variation, but here the variation is between 30–40%, but this is for very small speed value. But if you plot this in terms of production, then you see that the scattering is really obvious. Okay. And a final point is you see that the OD matrix evens influence the value of the capacity, because you see that the capacity of this reservoir increase when you increase the value of tau. So the main conclusion from the simulation study is that the mean overall distance L is a key variable to characterize the macroscopic behavior of a reservoir, and this variables is very sensitive to the OD matrix, and it is also influenced by the traffic conditions. I mean the number of vehicles within the reservoir, and the reason is that because I use a Randolph equilibrium condition, when the accumulation increase, the vehicles tends to use routes with a longer distance just to equilibrate the different alternatives between one local origin and one local distribution, and this tends to increase the value of L. So you have a double influence here, an influence depending on the OD matrix and also an influence depending on the traffic condition within the reservoirs. And finally, the OD matrix also influences the MFD shape to a lesser extent, but still, and especially in congestion. And this is, of course, here I have used a very wide variation of the OD matrix, and this is not what you will observe in reality, but the preliminary works on the MFD state that the MFD is independent on the OD matrix, and my simulation results show that this is not true, especially when you have a wide variation of the OD matrix. Now, I'm going to switch to the second part of my presentation, and I'm going to show you how we can try to refine the description of traffic dynamics within a reservoir using a multi-route macroscopic model. What I would like to say is that there is previous existing works about simulation using the MFD, especially from the research group of Professor Geroliminis, and also previous works from the University of Delft. But these preliminary works, previous works, show how to couple multiple reservoirs to perform a global simulation of a city. In my case, I'm going to focus on a single reservoir and to see how we can improve the description of traffic dynamics within the reservoir. And the idea is that you can couple my description of the reservoir with the global description that have been previously proposed in the literatures to have a full MFD simulators. So the modeling framework is the following. Let's consider a reservoir, and the idea is to improve the description of the parameters by distinguishing different origin and destination. And the idea is that we are not going to focus on local origin or local destination, but define what can be called macroscopic origin and macroscopic destination that correspond of part of the parameter borders. Between each macroscopic origin and each macroscopic destination, you can define a route for the vehicles that go from this origin to this destination. And if you look, and the idea is to distinguish all these macroscopic routes. Of course, what you have here is that all the routes may have different lengths. So this is the reason of this these figures here on the top right corner. You see that you have all the routes with an independent tracking of the accumulation and the speed, and you see that all the routes have different lengths. The idea is that I'm going to use a single macroscopic fundamental diagram to describe the traffic state within the reservoir. So all the speed will be the same, and you can use a classical conservation equations to describe the traffic dynamic within each macroscopic routes. To solve the system, the first step is to perform what I call the space normalization. The idea is to use a transformation with introducing the epsilon I variable, which is simply the ratio of the maximum length of the longest roots divided by the length of the current roots, and simply to perform here change in the variables to introduce x prime. The idea is simply to have all roots with the same length, which is the space normalization, but in that cases you will have different speed. So if you use so you can easily show that you can express the macroscopic value in the new referential by using this transformation. And what you will have in terms of equation here is the equation in the classical is the original equation, and when you perform the spatial normalization, you have this second equation, which is a conservation equation with now difference. So you have all the same space, but here you see that the speed will be equal to epsilon I multiplied by V n prime. Capital V is simply the macroscopic fundamental diagram that represent the traffic states within the reservoir. So what is really interesting is that you can express this as a system of hyperbolic equation, and you can easily derive the conservative form. And this is this is the equation of the conservative form of this system. And what is really interesting is that this system has been studied before, because it has been studied for multiclass model for classical link traffic flow theory. The idea is that when you have a single link with a different vehicle class, you have different speed for each class of vehicles, and when you perform the spatial normalization, you switch from a system where you have the same speed for all vehicles but different lengths to the same length with different speed, and then you have exactly the same system of equation. And because the system has been already studied in the literature, we know that it is well posed, and that you can that the system the solution have all the appropriate properties to derive a numerical scheme. So so now we need to perform the simulation, because this is our main objective. We need a numerical scheme. So the idea is simply to use a Godunov scheme, but for a hyperbolic system. So we are going to derive the travel distance into small cells, which are not real cells, but numerical scale. It looks like numerical cells that are useful to derive the numerical solution. But what we really want to describe is not what happens within the reservoir, but what's happened at the boundary of the reservoir. So we want to have a proper description of the inflow and the outflow. So this numerical scheme and this numerical cells and this numerical scheme will be mainly useful to ensure a proper propagation of the wave within the reservoir. So here I have applied a Godunov scheme, and of course, because we speak about a Godunov scheme, we need to use the Riemann solvers to compute the flow at the cell boundary. And here I have proposed to apply Arten-Lax-Van Leer Riemann solver, which has never been used in this context, even for multi-class models. And the idea of this scheme is that it's quite simple, but its help is quite accurate if you can properly estimate what's how the current wave propagation within the cell. So on the bottom left corner of this slide, you see the analytical solution between two cells, and the idea of the HLL Riemann solver is to simplify the wave family by using only two waves that have the highest speed. So capital SU is the highest speed for wave of the first family, and capital SD is the wave speed for the second wave family. So in that case, we only have two classes, that means only two macroscopic roots, but this can be generalized easily for any numbers of macroscopic roots. But it's simpler to show the derivation with simply two macroscopic roots. So I'm not going to go far within the detail of the numerical calculation, because it's not easy to present, and all the details are included in the paper. But the key here is simply to find a proper estimation of the fastest wave, capital S U and capital SD, and for that I have applied the Gauss-Green-Sekel theorems to line and row of the matrix A to derive a proper bound for the wave speed. So this is why, thanks to this approximation, that the numerical scheme provide very accurate result, and as I'm going to show in the next slide. So let's look at two illustrations of this numerical scheme. So here we only have two OD couples, that means two macroscopic roots. Let's consider that you have the first travel distance for the first OD couple, which is equal to 500 meters. The second travel distance for the second macroscopic speed is macroscopic route is 200 meters. And when you perform the space normalization, the length is equal to the maximum one, so that means 500 meters. So I'm going to use 80 numerical cells to derive the solution. So here is the situation I'm going to consider. So you have here the reservoir with an accumulation equal to 30. The boundary, the downstream condition, which correspond to the outflow, has an accumulation which is exactly the same, 30 vehicles. And the idea is that you consider here a change of the accumulation upstream. That means just like increasing the demands on for the route 1, and at the same time I'm also increasing the demand for the route 2. So you have a switch between 30 to 40 for route 1 and to 2.5 to 15 for route 2. And you see on the right here the outflow. Sorry, just want to show you. So what you have here in color, you have the evolution of the flow provided by the numerical scheme. So you have in red what's happened for the total flow, in blue what's happened for the route 1, and what happened for route 2, which again correspond to the outflow, which is what I would like to represent. And the black color below and the gray color below correspond to the analytical solution. That in that case is if I have only two macroscopic roots, I can solve the hyperbolic system of equation analytically, and I can know precisely what should be the lag between the change at the entry and the change at the exit. And what I observe here is that the numerical scheme is able to properly represent this lag, and you have very well representation using the numerical scheme of what I should expect. And in particular, you see that you don't see the increase of the outflow before approximately 10 seconds, which is the time needed for the vehicles to that enters the increase in the demands that start at time t equal to 0 is observed at the exit starting from time that is higher than 10 seconds. You can see exactly the same things if you change the exit flow value. Like, for example, if you consider that there is a congestion coming from downstream that starts impacting the reservoir, and again, you see the evolution of the analytical solution in black, and you see in red, blue, and green what the numerical scheme provide, and you see that you have a very good fit between the two. Finally, I can show you an example. I was thinking that I have a more complex example, but not in this presentation. In the paper, you can see maybe it's here. So it just here you can see a more complex example with 4 macroscopic roots. And again, this figure are not easy to understand. This is 5-state diagram within the reservoir, but the most important here is to see what happens at the exit, and what you see here is again that you have a real improvement in terms of the representation of the wave propagation within the reservoir. So this concludes my presentation. The idea of this new modeling frameworks is that it's able to account for multiple macroscopic routes inside the same reservoir, and this definitely improves the wave propagation. But there is some obvious drawback, and the main one is that when one destination becomes congested, because I'm use a single macroscopic fundamental diagram to represent the internal traffic states, there is an immediate correlation of the congestion for all destinations. So this can be easily reacted by changing the expression of the macroscopic fundamental diagram, and in particular to make the macroscopic fundamental diagram depends on the accumulation, not the global accumulation, but the accumulation of in all routes. But this, of course, will include higher cost in terms of calibration. Here in the simulation I have considered a constant travel length, but it's quite easy to make it dynamically change depending on, for example, the OD matrix or the internal traffic condition. And final improvement provided by this framework is that because you have different macroscopic routes, this makes easier to track the level of heterogeneity within the reservoir, because you can just, for example, look at the distribution of the n value on the different routes, and this may be interesting to couple this representation with extended definition of the macroscopic fundamental diagram that accounts, for example, of the standard deviation of the density within the reservoirs to update the shape of the macroscopic framework. Of course, there is lots to be done to before we can use this framework for practical application, but I think this is promising directions to improve the MFD simulators. I have finished my presentation. I will be happy to answer any kind of question.
Thank you, Dr. Leclercq. Very rigorous presentation and a very nice work. So for those who have questions, now you can unmute yourself and speak out, or if you prefer to use the chat box, so you can type your question inside the chat box, and make sure you send your question to organizers and then panelists only. Again, organizers and panelists only, and that can be selected in the drop-down box on the bottom of this chat panel. So, is there any questions? I hear someone's talking in the background. Do you have questions? Okay, maybe some background noise. Okay, so So, Dr. Leclercq, maybe I can start with some questions and just to pre give some time for the audience to prepare for better ones. I really enjoyed your talk and thank you for the nice talk and I appreciate your great work. And so, um,
Thank you.
right now, actually, I see with a couple of IOD pairs and you have analytical relative analytical solution to the um, uh, to the final to this problem. And as the I if you see the OD pairs actually increase, do you see a problem of the curse of dimensionality, or is there a way of combining some of the ODs and reduce the dimensionality and still utilize this work to describe the realistic situation with many OD pairs?
Okay, two answers. The first one is just how you can set your network representation. The idea is that you have to define, if you look at your reservoir, how many macroscopic origin and how many macroscopic destination you want to represent, and this will define your macroscopic routes. And the macroscopic routes gather a lot of real routes that go from the same origins to the same destination. Now, in terms of solving the model, the point is that I'm only able to derive the analytical solution if I have only two macroscopic routes, because this is a classical problem when you look at hyperbolic system. It's the analytical solution complexity increase with the number of equations, and it's become intractable analytically. So I simply use analytical formulations to show that my numerical scheme is very very efficient, sorry, when the number of macroscopic routes is equal to 2. But the numerical scheme is generic, and you can use it with any number of macroscopic routes, and there is no proportionality with no real proportionality with the number of routes. This, of course, you increase the number of equations, so you increase the number of computation, but it is very efficient in terms of computation and can be used with lots high number of routes.
Oh, thank you. So I guess Dr. Jorge Lava has a question on the chat box. So can you read it?
Yes. I see the question and I will answer with pleasure. First of all, I will say hello to Professor Jorge Laval, which is a good friend of mine. Okay, so in my presentation, I definitely skip the south term because I consider there is no internal traffic sources within the reservoir. So after this slide, everything is equal to 0. But what I would like to mention here is that in terms of equation, because I have a direct representation of the travel distance within the reservoir through the variable xi, then I can consider source term anywhere within the reservoir. And in that case, you have exactly what you have with multiclass models. At each numerical cells, you can include some inflow and outflow and just update your equation. So this may be definitely didn't investigate this direction, but my guess is that this may also help to introduce, for example, some internal bottlenecks or internal measures source terms within the reservoir without very easily and very efficiently.
Okay, thank you. Any other questions from the audience? Okay, a follow-up from Jorge.
Yes, it's a flow.
So it's like a variation of a flow, or
It's really like a source term when you look at the classical KW dynamics. Usually you have the conservation equation equal to 0, and then you introduce a source term. So it's a flow per second and per meter. No, this is definitely not a distance. This is an inflow. Maybe the notation of d is confusing, but what I say, the distance is xi. So I mean that I can introduce my source terms anywhere, and especially use discrete source term for given xi, especially within the numerical scheme. But this is not a distance. The distance is x.
okay.
So Jorge seems pleased with my answer, so I'm happy.
Yes. Follow up this question. Actually, I sort of missed what epsilon I term is.
This is the epsilon I term is related to the space normalization. You see.
Okay.
So the original equations is the following, but if you look at the original equation, you have different lengths for different macroscopic roots, and this is not convenient for for solving the system. So by performing the space normalization, I can use exactly the same length for all macroscopic roots, but this is an equivalent length. But
Okay.
in that case, this changes speed, and what I simply do is to use a space normalization that guarantees that travel time remains the same. So if I change the distance, I change the speed accordingly to keep the same travel time.
All right. Thank you for
And
clarification.
This is the reason for epsilon I.
Great. Right. Any other question from the audience? Okay. If not, let's thank Dr. Leclercq again for his very nice presentation, and thank all of you for attending this webinar. And the next webinar will be 2 weeks from now, so stay tuned. I'll send out an announcement. Well, this adjourns this webinar, and hope you all have a great weekend. Thank you.
Thank you very much, and thank you for the organization and for making this real every 2 weeks. It's a very good thing for our community.